Hi, I'm Reese Goldside from Autodesk Research. In this video series, you'll learn how to use our new Dynamo package called VASA. We'll go through all the examples that are included in the software. In this first video, part one, we'll check out the overview example you see in this image. But first, let's make sure you know what VASA is and how to install it. So VASA stands for Voxel-based Architectural Space Analysis. That's exactly what it is. We're doing space analysis on architectural designs using voxel models. Here's an example of a voxel model. This was not done in VASA. This is a Minecraft model I found on YouTube, but it shows you the kind of representation we'll be working with using VASA. So the idea is you take your design, you voxelize it, then you perform a number of analyses on the voxel model. And you can do this for several design options. Because the analyses are voxel-based, they tend to be fairly approximate, but they should be suitable for the early design stage, like for generative design, for example. The analyses you get with VASA are direct daylight and shadows, visibility from a point, travel distance from a point, and 3D pathfinding. You also get the ability to voxelize geometry. And finally, you get surface, solid, and fill operations specifically for voxel models. These operations help you prepare models for analysis. They also let you take the results of your analyses and further process them. Okay, so let's see how to install first Dynamo and then VASA. For Dynamo, make sure you have some relatively recent version of Revit installed. Then go to dynamobim.org, click Get Dynamo, and you'll see several options. Dynamo Revit should already be installed on your machine. You access it via Revit, and you could use VASA within Dynamo Revit if you want. In this video series, I'll be using Dynamo Sandbox. So if you want to use Dynamo separately from Revit, go ahead and download Dynamo Sandbox. And there's two things you need to remember. First, use 7-zip to extract the archive. Do not use the unzip tool that comes with Windows. So get 7-zip and use that. The other thing you have to remember is to use your high performance GPU. So go to the Windows search, type in graphic settings, load up the dialog box, click browse, find the Dynamo Sandbox executable, wherever you put it. I put the whole package on the C drive, and then click options, select the high performance GPU and press save. And then Dynamo Sandbox should be working. So you can go ahead and run that. And to install VASA, all you do is go to packages, search for a package, type in VASA, it should come up, and then you can install it. Right, and that's it. So I'm going to switch over now to Dynamo. You can see I've got VASA. You can see the VASA on the left there. So I've got that installed. And we're just going to make sure everything's working. So let's right click and type in sphere and select by center point radius, and that creates a little sphere at the origin. Let's double click now to create a code block. We'll type in 5 semicolon and connect that to the radius. So I got our sphere radius 5. And now we'll use VASA to voxelize it. So open up the VASA menu on the left, and then open up Core, Voxel Model, and click By Geometry. You'll get the voxel model by geometry node, and just connect the sphere to that node as the geometry. And then we're going to also double click and type in a 1, and this is to set the coarse voxel width parameter. So the coarse voxel width, we recommend it should generally be 1 meter or maybe 4 feet if you're using imperial, but usually 1 meter. So I'll assume we're in meters here, and we'll connect that. And now the sphere should be voxelized. But in order to see it, we need to a separate node. So scroll down on the menu at the left, and you should see the display voxels node. And then connect the voxel model to that node. And if you're new to Dynamo, Control B switches mode so you can navigate and zoom in on the geometry, and you can see the sphere is voxelized. And Control B switches back to the graph mode. All right, so very simple example. Now let's see something a little more interesting. So we're going to bring up the first example that comes with the VASA package. To do that, we'll need to find the directory where VASA was installed. So if you're using Dynamo 2.11 or earlier, you want to go to Packages, Manage Packages. If you're on Dynamo 2.12, I'm on 2.12. We'll go to the Dynamo menu, click Preferences, Package Manager, Installed Packages. There's VASA, 3 dots, Show Root Directory. And then I'm just going to click on that path and copy it. I'm going to go and close everything here, and then go File, Open. I won't bother saving. I'm just going to paste in that directory where VASA is installed, click Extra, and those are all the examples. So let's go ahead and load the first example, 01 VASA Overview. And that'll take a few seconds to load. It's going to do all the calculations. And we should start seeing some things appear. Okay, so when you load up a new example, what you want to do is first check out the description. So here it's just telling you that the point of this example is to demonstrate the main analysis features of the VASA package. There's also some additional comments you'll want to check out. In this case, it's suggesting that we start by toggling on and off the display nodes at the right-hand side of the graph. So we'll zoom out, see the whole graph. The display nodes are these ones in blue on the left, on the right, sorry. And what I'll do is I'm just going to actually select all of them and hide them all. So I got them all selected. I'm going to right click, hide all geometry preview. And I'll turn them on one by one. So first, display building and context voxels. I'm going to right click the node, press preview, turn it on. So now you can see the voxelized building geometry. Let's take a little look at that. And the next node is display glazing voxels. And so here we're seeing the glazing. This is also a voxel model, but it's just displayed in a translucent color just because we selected that color for it. Now let's turn on the shadows. And now we're seeing the shadows cast by the building and the tree, assuming a certain sun direction. So we see the shadow analysis. I'm going to go and hide that, and we'll look at the view voxels. These are showing the views from a point. This is from a specific point in the building. And to see that a little better, actually, we're going to look deeper into the building. So I'm going to zoom out on the graph. We're going to find this slider up here, the crop depth. And if we increase that, it'll cut off the top, cut off a few more layers off the top of the model, allow us to see down into the second floor. I'm going to set it to 29, and that lets us see that point there. So this is the point that it's calculating views from. And I'm just going to move the point just so you can see it update. Here are the view parameters. I'm going to change the x coordinate of the point one way. There it updates, and change it the other way. I'm going to undo that. I'm also going to change the radius, so you can see it's only calculating views up to a certain distance, 27 meters. I'm going to increase that. I'll increase all the way. And now it sees all the way across to the other side of the building. Okay, now let's hide the visibility, and we'll show the distance field. So this is showing all the places that a person could reach within a certain distance from a point. And it's actually this point here. So to make that a little more obvious, let's go and find the distance parameter. And we'll set that really low to start with, 1.5 meters. And I'll increase it slowly, 4 meters. And you can see the distance field's expanding, 7 meters. And then it goes up and down the stairs. So actually, let's zoom out on the graph and put the top back on the building so we can see it go onto the 3rd floor. Just rotate a bit. And we'll go back to that distance slider. It's about 11.5 meters. We'll increase it, 14 meters. And you'll start to see it go onto the 3rd floor and onto the 1st floor. And there's a door there, so the distance field goes out the door. Okay, let's hide that. And take a look at the path. So here's a path that's being computed in 3 dimensions. From this point here, just beyond the tree, to a point on the 3rd floor in the building. And so it figures out, that it should go in the door there. And then figures out that it should use these staircases to get to the 3rd floor and get to the point. Okay. I'm going to hide that. All right. So now what we'll do is we'll start going through the graph in a little bit more detail and look at the intermediate calculations, intermediate geometries, and voxel models to understand how this works. So I'm just gonna hide everything, and we'll start way back on the left of the graph. So the input geometry comes in 2 forms. VASA can either voxelize geometry in triangle format or in just regular Dynamo geometry format. So for the triangles, in this example, it's getting triangles from 2 STL files that have all the building geometry in them. And there's VASA nodes that can import STL files. And so we get these 2 sets of triangle, well, 2 lists of triangles. You can see actually they're just flat lists. Those first 3 points are the X, Y, and Z coordinates of the first vertex of the first triangle. To see what that looks like, if we go to the VASA menu over here and go to utils and triangles as 9 numbers, we can create a 2 mesh node just to see what this looks like. So here's the building geometry from the triangles, and looks like this. And here is a separate set of triangles for the glazing. The reason why we handle glazing separately is because we want to exclude the glazing when we do visibility calculations, because you can see through a window. But we want to include the glazing when we do pathfinding, because you can't walk through a window. Okay, so that's the triangle data. And then we also have some regular Dynamo geometry. So we've got a cuboid, a cylinder, and a sphere that's all going into this list. I'm going to turn this on. So you can see the cuboid is representing the ground, the cylinder is the trunk of a tree, and the sphere is the foliage of the tree. So we have this list of 3 objects. And if you're using Revit, for example, you might have a very long list of solid objects, but you'd process them the same way that we're doing as we're doing here. So let's turn that off. So all that input geometry is going into these voxel model creation nodes, a voxel model by triangles for the STL data, and voxel model by geometry for for the objects. You can see all the nodes are being given the same coarse voxel width. Remember that we recommend 1 meter for that parameter. It's important to know what units you're using, and this example happens to be in millimeters, so 1,000 millimeters is 1 meter. So that's the parameter, and we create a bunch of voxel models from that. Let's take a look at them. So let's create a display voxels node. Actually, I'm going to right click and just type in display, and it's going to come up here, display voxels. So we can look at these voxel models one by one. There's the building geometry. Here's the glazing. And here is the context geometry, is the 3 objects. And you'll note that for the geometry, it's creating a separate voxel model for each object, one for the cuboid, the ground, one for the cylinder, one for the sphere. So what you do then is you want to union them. So you use this union operation that comes with VASA to turn that into one voxel model. And we're actually using the union again. We're taking the building voxels, we're taking the context voxels, we're excluding the glazing, and then using this to create a voxel model for union. I'm taking the union again and using this to create a voxel model that we use for all the visibility calculations. So this is what we use for visibility. Notice that everything's there except for the glazing. Oh, so something I should point out. Sometimes you notice these funny artifacts as you're looking at a voxel model. There they are. That's nothing wrong with the calculations or the voxel model. This is just an artifact of the rendering. What VASA does is it internally groups voxels together into these 16 by 16 plates. And for some reason, you can sometimes see them. Again, if you're seeing these artifacts, they usually go away when you navigate, and it's not a problem with the calculations. All right, so let's see what that's being used for. So we create this voxel model for visibility, and if we follow this link here, we're using it first to calculate direct daylight. So here we've got this visibility from direction node. So I'm going to show you where that is. So in the VASA menu, it's under operations, visibility operations, visibility from direction. And I'm going to create a display node, display voxels, just to show you what that looks like. And we can't really see what it looks like yet, but what we're going to do is we're going to right click, type PAL to bring up a color palette. I'm going to select color yellow, and I'm going to make it quite translucent so we can see through the voxels a little bit. Okay, so there's the visibility from direction calculation. We're actually going to turn on the building voxels. Now we can, so this tends to look good from the inside, so I'm going to try to go into the building if I can. Yep, whoops. Sometimes difficult to navigate inside a building. There we go. So you can see the daylight coming in through the windows and through the skylights. But of course, it doesn't look like much on the outside because it's kind of everywhere. So what we'll do now, or what we do in this graph, is we invert it. So we take all the voxels and all the empty ones become filled, and all the filled ones become empty, and that ends up showing us the shadows So let's see what that looks like. I'm going to change the color to purple. And now we can see the shadows, the regions that are not visible from the sun direction. And we're seeing some Z fighting there. That's because the building voxels are not visible from the sun, but so they're showing up as shadows, but then you're getting Z fighting between the building geometry and the shadow voxels. So what we're going to do now is we're going to use the subtract node and we're going to take the shadow voxels and subtract off the voxels that we're using for the visibility calculation. We're going to subtract off the building voxels. So let's see what that looks like. And now the Z fighting is gone because the shadow voxels are not including the building and context voxels. Okay, just to show you where those operations are. If you go, so again, under VASA operations, solid operations, there's a union operation that we saw before. The invert operation we use to convert the direct daylight into shadows, and the subtract operation that we use to subtract off the building voxels. So these solid operations are quite important. Okay, so that's about it for the shadows. I'm going to delete those nodes, and I'm just the only difference here, if I turn on the final shadow voxels here, the only differences are that I'm choosing a translucent color, but also the shadow voxels are going through this resize nodes. What's happening there is, remember we had this crop slider, so that crops one of the voxel models. But then we take the extents and we resize all the voxel models before displaying them, so that they all get displayed with the cutoff at the same elevation. So that's what these resize nodes are doing. All right. So let's leave it there. I encourage you to go through the rest of the example and look at the intermediate calculations and familiarize yourself with how that works. And then if you want, you can check out the other videos in this series where we'll be going through all the other examples that are included in the software. So check out the description of the video, and you'll find links there to the other videos. Okay, great. Thanks for watching.